Okay, so let's get started with the series excited DC motor. We studied the separately excited DC motor. Now we will focus more on the series excited DC motor. Well, in the series excited DC motor, you'll find that the field of the DC motor is connected in series with the armature circuit. So you'll find that we have LA plus LF. We have two inductance, one for the field circuit and the other one for the armature circuit. If we add them in one inductance, will be fine, no problems. The modeling for the circuit will be fine, and also the RF and RA will be separated with different resistances, with different inductances. But on the circuit model, we can just add them together, no problem, because they are in series, right? We have without any problem. The field circuit was also designed in a way to tolerate the armature current, okay, and the steady state average can be obtained, as we'll see now. But the key point is here, the armature current and the field current are the same current in reality. So here we have IF and IA, the same value. The same thing here, you'll find that the field circuit is designed also to apply a magnetic field in the motor. Without this magnetic field, the motor will never work, right? So this is important. In the separately excited motor, you'll find that this connection is a separated circuit, but in this we have the same circuit, no problems. The only difference, which is important, IA is equal to IF, because RA, LA, RF, LF are connected in series. Now, if you look at VA is equal to how much? The voltage here is equal to the voltage applied on this resistor, the voltage applied here, and the voltage applied here, right? So this will be RA plus RF times the current, which is IA or IF, no problems, plus LF plus LA, again DI by DT, DIA by DT, plus EG. On the steady state condition, we agreed that this will be 0 because there is no change on the current. The rate of change of the current is equal to 0. So VA is equal to how much? RA plus RF times IA plus EG. Now again, the relation between the mechanical and the rotating part. So EG is equal to how much? KV, the angular speed, times IA, or IF, right? Because in this motor we have the same value, so we said IA, no problems. If you remember last lecture, we said EG is equal to how much? EG is KV. It was for the separately excited motor. EG is equal to how much? KV omega IF. So this is the original definition, right? But here we can put IA, no problems, because IA and IF the same value, so we have no problems at this point. So EG is equal to KV omega times IA, and the developed torque TD is equal to how much? KT times IF times IA, without any problems. Now from the rotational equation of motion on this part, we have the developed torque, and this developed torque must be equal to how much? Again here, TD is equal to how much? B times omega, friction B times omega, plus the load torque TL, right? The inertia J, change of the speed, the acceleration d omega by dt. At the steady state condition, this will be how much? It will be 0. So we'll be left with this equation, TD is equal to B omega plus TL. Now let's go for VA now. Come back to VA here and substitute EG in this equation, okay, and see how we can obtain the speed omega. VA is equal to how much? RA plus RF times IA plus EG, which is how much? EG KV omega IF, right? From this equation you can say omega is equal to how much? VA minus RA plus RF times IA over KVIF, right? Now, since we have the same current on the field and armature, so how we can control the speed? So by either changing the armature voltage, VA, right? Change this, then you will be able to change the speed, okay? Or if you change what the armature current, IA, which is again is the field current, then you will be able to change the speed, right? Now, if you try to find the relation between this, draw the relation between the torque, power, and the speed, current, armature current, and the speed, let's see what happens. But we said that the armature current is a measure of torque demand. So the torque indicates that a series motor can provide a high torque, particularly at starting. That's why series excited DC motors are commonly used in traction applications. Now let's draw the relation here. So here, this is the torque. At the beginning we said IA is constant, which is IF, but at the rated speed, at the VA rated, you'll find that here the speed omega IA starts constant IA. Then after certain speed, IA must be controlled, must be reduced to make sure that we are operating at the rated conditions. Here the same thing, at the beginning we have increasing power, then the rated power here, the developed power rated. You'll find that here we have VA rated, the rated voltage, okay? Here VA is increasing at certain point. When you want to reach your rated condition, so VA must be the rated value and the power be constant. The torque at the beginning, when you start moving the motor at the beginning, of course the torque will be how much? It will be very large, the maximum, right? Because thing is constant, not moving, need large torque, right? So this is the developed torque must be maximum. At certain point, when the motor reach to the rated condition, you'll find that this torque start decreasing to be minimum. Okay, so this is torque TD, and this is the power PD. After that, after we reach to the rated condition, you'll find that the speed torque relationship flows natural characteristics of the motor. Here again we said this is constant torque, and here we have constant power, right? Constant power. Now let's move to the mode of operations for this motor. Okay, how can we control with the field current? As we said, we can change either the voltage via armature voltage or the field or the armature current, right? So we have some arrangements that we can use in order to make either motoring, like increasing the speed, or braking. We have several types of braking, how to stop the motor of moving, how to stop the motor from moving. And then you'll find that we have either the regenerative braking, we have dynamic braking, or what we call plugging. Okay, so let's move now and see the mode of operations for this kind of motor. Here now at the input here we have, if you want to work in the motoring mode, just the normal condition, what we look at is the voltage VA. Okay, VA, just DC connected to this circuit, and this is connected here. Okay, now you'll find that IA and IF we have the same current. Okay, let's say this point is, let's say this is F1 and this is F2. Here we have A1 and A2. Okay, and this is the field current, or IA. The armature current will be same at this point. And here EG is plus minus, so the motor is speeding. In the motoring condition, of course, EG is smaller than VA. Okay, because the input voltage, the armature voltage, is giving the motor is increase its speed, or it's speeding, it's working. Okay, so the voltage here plus the voltage on the armature resistance, on the inductances, all these will be equal to VA. So VA definitely will be larger than EG. Okay, and both IA and IF are positive on the same direction. Okay, and the motor develops torque to meet the load demand without any problem. Okay, now let's go for the second mode of operation, which can be considered as what we call the regenerative braking. What we do actually is we reverse the connection, okay, of the field circuit. So here we have VA, and this is, as you said, this is F1 and this is F2. Okay, what we do actually, we connect this one here, okay, and connect this one here. Okay, and this is plus minus EG. Okay, for the regenerative braking, so the current EG now is start like decrease its speed. So this is A1, this is A2, and the current will be taken from the motor, so this will be moving here. Okay, so this IF will be in this direction, and IA, which is equal to IF in this direction. At this point, IF is how much? IF is positive, right? Positive IF. Inside the field coil, okay, the field circuit, IF is the same direction, no problems. But within the armature circuit, IA, which is the same in value with IF, is in the opposite direction, to be negative. Okay, negative, because the motor is giving, not taking. So the motor acts as a generator at this point, okay, and develops an induced voltage EG, okay, and EG at this point is greater than VA. IA is negative and IF is positive. So this is what we call the regenerative braking. We can use this one, of course, like if you have a train, and this train, instead of, like, you can charge your batteries while you are not motoring this train. If you want to brake, for example, you can use this energy to charge the batteries, which is interesting and important. Okay, you can save energy. The other thing will be similar, what we call the dynamic braking. Dynamic braking. And here, instead of the battery, we connect a just resistor. You can generate heat from this, okay, which is also can be used for air conditioning. Here again, this is connected. This is again, this is F1, this is F2, A1 and A2. This is connected in the reverse direction. Again, IF will be positive, IA will be negative. The voltage here is plus minus, so this is also braking similar. So VA is replaced with a braking resistance RB, let's say, and the kinetic energy of the motor is dissipated in a resistor. So this and this almost similar, but instead of the battery we obtain a resistor. The last mode of operation that we can explain here is what we call the plugging. Plugging is a type of braking. So the connection, it will be like this. So this is VA plus minus VA. This will be connected in this direction. Okay, so IA, it will be like this. This will be connected here. Okay, at this point we reversed EG. Okay, so this is EG at this point is giving negative voltage, and this is connected in the reverse direction. Okay, so this is F1 and here we have F2. This is A1 and A2. So we have our F. So IA and IF, of course, in terms of value, they are the same. Here, the key point is the armature terminals are reversed while running, or the field terminals, not both. So you can either change the armature terminal, or you can reverse the armature terminal or the field terminal, because we need this to be giving negative voltage. So now VA and EA act in the same direction. So you can see this is minus, plus, minus, plus. So this as if we add them together, so they act in the same direction, and the armature current is reversed at this point, because look, IA in this direction but EG in the opposite direction, so armature current is reversed, and this will definitely produce a braking torque. IF then is positive, no problems. So you can either reverse field terminal or the armature terminal. So these are the four common mode of operations in this kind of motoring. And then we have three types of braking: regenerative braking, dynamic braking, or plugging. Now let's go in depth and see the four quadrants of operation, like the relation between the speed and the torque, okay, and see how the circuit can be classified. So here let's say that we have the torque, positive torque. Here we have positive speed and torque. This torque can be positive, negative, speed can be positive or negative. And draw the circuits which are related to this. Now if we have forward motoring, then we expect that VA is greater than EG, no problems. So here the circuit can be something like this. So I will say this is EG plus minus, this is RA, and here we have VA also plus minus. So the current is in this direction, IA, and IF in the same direction, and at this point EVA is greater than EG, and this is what we call forward motoring. The opposite of this one, what we call what? Reversed or reverse motoring. Okay, reverse motoring, where VA, the absolute value for VA, is greater than EG, and then this will be, the terminal will be reversed, and also this will be reversed. You are moving in the opposite direction, as it's the same circuit, right? But the direction of the motor will be reversed. So this is the reverse motoring. So this is EG plus minus here, and this is VA plus minus here, and the current will be on in the opposite direction. Okay, so this is IA. So this and this, we have the same circuit, but the direction of the current on the opposite direction. Now let's move to the braking here. With the forward braking, we expect that what? The torque in the opposite direction, the speed, okay, the torque is negative, but the speed is positive. We have VA here, plus minus VA. Here we have EG, same signs without any problem, because the speed is positive. Still, we have positive speed, okay, plus minus EG, and the current in the opposite direction. So that's called what? Forward braking. So this is IA, and this is VA, EG, and VA, of course, as you expect, is smaller than EG, and this is what? Forward braking. Now the last quadrant. So let's say that this is the first quadrant, this is the second quadrant, here we have the third, and here we have the fourth quadrant. So the fourth quadrant, what we call the reverse braking. Again, VA is smaller than EG, but the direction here will be different. Okay, so this is EG minus plus VA, right? and RA, EG minus plus, everything in the opposite direction, IA in this direction. Here's braking, the torque is positive, but the speed is negative. So as if we are in the opposite direction. Braking, but in the reverse direction. So these are the four possible quadrants, the four possible operations, either motoring or braking. The motoring can be either forward or reverse. The braking also can be either forward or reversed. I hope that you enjoyed this lecture, and I will see you next week.